accurate determination of the redshift just by looking at how the spectral lines shift. So, so you can get a very good quality spectroscopic redshift for this. But yes.
I have a doubt.
Yes.
How do we know if this change of the spectral line of the galaxy is due to the redshift and not indeed proper movement of the galaxy?
Yes, you don't. So in the end, it's a composition of the Hubble flow, let's say, and proper motions. Okay. If you are far away, if you're looking at galaxies that are far away, the Hubble flow is large, and the proper velocities are small. So if you're looking for very distant galaxies, you can almost neglect, not quite, but almost neglect the proper motions. Now, if you're looking in galaxies that are nearby, then you have to be a little bit more careful. And in fact, maybe you have seen these figures of the first surveys of galaxies. They saw elongated configurations of galaxies nearby, which were called fingers. I hate these things, but some people call it fingers of God, you know. This but this is just a fact of proper motions, really. Yeah. So, so this is the type of a survey that was, for instance, done in this Sloan Digital Sky Survey, which was one of pioneer experiment doing these things. And then it was continued. There was several generations, and then finally something called BOSS and eBOSS. And then maybe people already, I think I saw posters of people using data from eBOSS to measure some things. Maybe it was you, right? So yeah, so this is great. The data is public, people can use it to measure things. And so what is the technique? The technique is that you have to take the light from a galaxy. How do you take light from a galaxy? First, you have to know where the galaxy is, so that's a problem, right? And the way Sloan Digital Sky Survey did is that they knew where the galaxies were at some night in the sky. They got a plate, a metal plate. They drill holes on the metal plate where the galaxies would be, and then like 500 holes in one metal plate, like this big. And then they attached a fiber cable to each hole. And the fiber took the light from the galaxy to a spectrograph. So this is amazing, no?
They did where the galaxies were from other surveys.
Yes. So they need to know beforehand where the galaxies are. That's okay. They have to know. And the successor of this eBOSS is called DESI, is the Dark Energy Spectroscopic Instrument. So there'll be many acronyms. Yes. So there'll be many acronyms here, and if I don't say what the acronyms mean, just ask again because I may forget. Okay. So DESI is the Dark Energy Spectroscopic Instrument, and there's a group in Latin America working in DESI. I don't see the person here. So it's a group from Colombia. America is also in DESI. So there are two groups. This is this is great because, you know, joining these large experiments is not easy. And I think finally Latin America is picking up and joining these large collaborations. It's like joining CERN, okay? It's amazing. It's really nice. So DESI has a group in Mexico. Yes. So what's the name of the... Yes, Brenda. Okay, thank you. And then the group, there's a person in Mexico, I forgot the name. Mariana Vargas. Yes, very good, very good. So there's a group in Mexico and there's a group in Colombia. Did you know that? There's a group in Colombia. Did you know? Jaime Ferrero is the name. So this is important. It's important for people to know other groups in Latin America. And this is, okay, I put the hat of the association now. That's a role of this association, to put the groups together. Okay, sorry about that. So it's very good that you're working in DESI. So DESI is the spectroscopic survey, which measures redshift. And DESI is already taking data, is doing extremely well, and already, so it started what, last year, maybe 2 years ago, and already put out publicly the first early data release with more, I think it's 2 million galaxies. Correct me if I'm wrong, Brenna. It's like 2 million galaxies. 2 million galaxies in 1 year. This is what eBOS, Sloan Digital Sky Survey, eBOS, etc., took in 20 years. It's amazing. It's just incredible what they're doing. They don't use plates. Brenna can explain much better than I do. They use robots to position fibers, and it's not 500, it's 5,000 fibers, and they put the fibers on top of where the galaxies are. So this is incredible. It's amazing. So these are called spectroscopic surveys. Okay, they take light and take the spectra, but they don't really, you understand, they don't see the galaxy. They just take the light. So there's no information about the shape of the galaxy and things like that. But they have very precise information about redshift. This is amazing. Okay, so the other type of survey is called photometric survey. So photometric surveys, they do not take spectra directly. Okay, what do? They take pictures. They take photographs of the sky, and then all the galaxies are there. We don't need to know where they are beforehand. Just they're there. And they take these pictures in different filters, like 6 filters, typically 6 filters. There are surveys with more than 6 filters, but typically 6 filters. And, and with this information about colors of different filters, we try to estimate the redshift. So the redshift determination is not very precise. So it's not precise. We can do cosmology, but I show you what we do. So it's a fair quality photometric. It's called photometric redshift because it's not as opposed to spectroscopic redshift. So it's a redshift estimated from pictures. Yes.
How about the determination of the photometric redshift
yes.
with respect to the spectroscopic redshift?
Right. Right. So there's some uncertainties, and we can quantify the uncertainties. And the uncertainty is around, I think deltas, the uncertainty in the redshift, it goes like, if I remember correctly, is 0.05 times the redshift itself. So, but there is a consequence for this, which I'm going to get to, okay? So for instance, we're not good at redshift space distortion measurements and things like that. So for F sigma 8, it's not very good. But on the other hand, we have a large number of objects because we don't need to know where the galaxies are beforehand. We just take pictures again. And also we have access to the images, the shapes of the galaxies. So we can measure the shapes. And this has some interesting consequences because we can estimate also the distortions of the shape due to matter and dark matter between us and the galaxies. Okay, so those are the two main types of surveys. Can I go this now? No, I cannot go like this. Can I? So I go this. Can I go like this? Oh, I go like this. Right? Okay, so this is some of the surveys that are out there. Actually, this is an old slide. So I'm going to show something more updated. This is BOSS and eBOSS. So so the colors. So the red colors here are spectroscopic surveys. The blue colors are photometric surveys, imaging surveys. Some of them have both, like Euclid. So you can see that these are very large projects and they're complicated, right? And this will teach you a lesson because if you look here, have you heard of Euclid? Who has heard of Euclid? Right, Euclid was just launched July 1st. If you look at this plot, you see where it was supposed to be launched? So this is real life, okay? This is what, it's actually incredible that it was launched because it was supposed to be launched in a Soyuz rocket. And then with the war, Russia and Ukraine, this has to be stopped. And then they had to find another space rocket to carry. And then Elon Musk stepped in, and so he went up on a SpaceX, what's it called, Falcon? I forgot the name of it. Falcon 9. If you look in the internet, you can see the launching. It's amazing. It's really amazing. So it's on its way to Lagrange point 2, right? Together with, it's going to meet Planck. I hope it doesn't really meet Planck, right? It's a huge orbit. Yes. So there are other things there too. No? What else? Okay, I think there are other things. Yeah, but not too much. Okay. Anyways, this is just to show you the difference. So this is DESI, which was also supposed to start in 2017. It did not. I think it started in 2019 or 20. I forget. When did the DESI start? Do you remember? It's something like this, yeah. And this is the LSST, which was supposed to start in 2021. It will start next year. And in fact, even changed its name. It's not a Large Synoptic Survey Telescope now. It's called the Legacy Survey of Space and Time. So we kept the acronym, but we changed the name. And then there's WFIRST, which is not called WFIRST anymore. It's called Nancy Roman Telescope, Space Telescope. Okay, so this is just yes.
Difference between the stage 3 and stage 4.
Right, it's the precision. It's so there was something very, I don't know if Julien participated. It was called the Dark Energy Task Force, which was organized by Rocky, was one of the main organizers. And they made this classification of stage 3 and stage 4, relying on something, on how precise you could measure some parameters. Okay, that's how the classification was done. So more technically, it was based on what we call Fisher matrix. I don't know if you ever heard of Fisher matrix. So it's a way of given some characteristics of the experiment and some assumptions, you can actually see what would be the precision that the experiment would be able to measure something. And this is how the stage 3 and stage 4 were classified. Thank you for the question. Okay, good. Yes. No, it's not full sky. DESI? No. They are, huh? Huh? None of them are full sky. First of all, they cannot be full sky because of our galaxy. So I show you what the area is. Just a sec. If I show you. So this is something a little bit more recent from, have you heard of this no-mass process that they do in the US? But again, this is more US centered and actually only projects that are supported by DOE and the NSF, which are agencies in the US, okay? So this is, the Rubin telescope is where the LSST will be taking data. This is DESI. There are also CMB experiments and gravitational wave experiments and 21 centimeter experiments. You can look up in this reference here for this no-mass process. So, so this is a picture showing the evolution of the surveys. So these are imaging surveys and spectroscopic surveys. Sloan Digital Sky Survey actually did both. They had the capability of measuring spectra and also measuring images. And this is the field of view, 7 square degrees, etc. So let's look at the imaging first. So the evolution was the dark energy survey, which we talk about, and the evolution of dark energy survey is the LSST, which I'm also going to talk about. And I'm not going to talk much about spectroscopy, sorry. Maybe you can tell us a little bit more. But also started with the Sloan Digital Sky Survey, and BOS and eBOS were all conducted here. And now DESI is the successor of this. And then there's some plans of a new spectroscopic facility after DESI. Because again, these things takes 20 years to be built. So you really have to plan way in advance what you want to do. And the way to decide is a community. Okay, it's a community-based, they have inputs from the community, etc. in the US. Okay, and this is more answering your question, I think. So this is a comparison of photometric surveys, and what is shown. So this is a slide I stole from Tim Eifler, so it's not my slide. And this is the different surveys. Photometric surveys, and the dark energy surveys here. There's the hypersuprime camera, Euclid, WFIRST, now it's Roman, LSST is here. So what is shown here is this one is the density of galaxies that your instrument is sensitive to. So for instance, DS, we have observed 10 galaxies per arc minute square in our survey. And here's your question about the area of the survey. Okay? So you can see that some of the surveys have pretty small area. So this is in square degrees. DS was 5,000 square degrees. No, how many degrees we have in the whole sky, square degrees? Something like that, 20,000, 24,000 square degrees, okay? So this is like 1/8 of the sky, more or less. 5,000 degrees is like 1/8 of the whole sky. And then your question is about Euclid is 15,000. It's not the whole sky, but it's pretty big. So Euclid is a satellite. So they have a way of looking at different regions. DESI is a telescope in the northern hemisphere in Arizona. It's called Mayal telescope. But she can say more. Have you been there? Have you been to Mayal telescope, to DESI? You should go. It's one of, I had no, this was amazing. Of course, I'm not an astronomer, right? But for the dark energy survey, they need people to go there and do shifts, like in experimental high energy physics. People go to CERN to do shifts, and I volunteer, of course. I don't know everything, but I volunteered. And you don't have to do much because everything is automatic, etc. You just go there, and you don't look at the telescope. I thought I would look at the telescope. You don't look at the telescope. Everything is automatic, and the CCD camera, etc., etc. And it was one of the most amazing experiences I had because the place is beautiful. It's in mountains in Chile. The sky is just fantastic. And yeah, you should try. Now, LSST will not have shifts anymore. I don't know if DESI has shifts, but LSST will not have shifts, unfortunately. Anyway, it was a great experience. Okay, so I'm not going to finish this lecture. In the following, I will focus on these two surveys, the Dark Energy Survey and the Vera Rubin Observatory Legacy Survey of Space and Time. So both of them are photometric surveys, and they share the same techniques. So you can say that the Rubin or the LSST is the evolution of the Dark Energy Survey. As I said, photometric redshifts are less precise than the spectroscopic redshifts. So we don't have a very precise three-dimensional information because the redshift gives you the third dimension, right, the distance. So what we do is that we slice the space in beams of redshift. So this is something we do, and then we perform. So these are called tomographic redshift beams. I'm going to talk a little bit more about this, and then we perform analysis in each of these projected. In each beam, with everything projected in the area. So it's a two-dimensional analysis. So you see that we do things that are very similar with what people in CMB do, because we are also doing like a spherical analysis, not 3D. Because every beam, we just do things beam by beam in the projected galaxies in that beam. So what we measure is angular correlation function or angular power spectra. And this is just an illustration of these things that we divide our survey into redshift beams. So this is an example where we have these redshift beams here. I show you some more about that. And then we make the measurements in each redshift beam. Okay, so a few words about the Dark Energy Survey. The Dark Energy Survey still is a collaboration of more than 600 members with 25 institutions, 7 countries, and it's only Brazil and Chile, actually, I should say, from Latin America. Chile, every telescope that's in Chile, Chile has Chilean astronomers, they have the right to participate in the telescope time. So we use a digital camera which was the largest one at the time, 570 megapixel camera. So it's just like a cell phone, right? Just it's more complicated than that, but it's just like a cell phone. Those are the CCDs, and these are the images that you can get in the camera. This is so this is in Cerro Tololo International Observatory in Chile, near La Serena. It's a very beautiful location. And the dark energy survey is in this dome here using the Blanco telescope, which was an old telescope that was refurbished in order to accommodate this large dark energy camera, and which is sitting at the focus of the telescope. And the CCDs are here, and then there's actually in front there's something to shift the filters. So we have 6 filters, and so it's a 4-meter telescope, and the full survey took 5.5 years from 2013. It finished in the beginning of 2019, and we analyzed data already for the first 3 years. And we are now in the process of finishing the analysis of the final amount of data, the whole amount of data. So this is coming out soon, the final analysis, hopefully in 6 months or so. So it's a wide field survey with 5,000 square degrees. That's the area that we're covering in 5 bands. It goes down to magnitude 23. And we have positions and shapes of more than 100 million galaxies. So it's really big data, okay? To explore all this data, it's not easy. Yes, and as I said, we are on the way to our final analysis soon. Okay, so I just give you a little taste of what we have done, and then actually I try to go into more detail in the last lecture. This is not the last lecture, lecture of yesterday. So maybe I should go faster. So the data was first included in this so-called year 3 catalog with 345 nights. I think I will not go into detail, okay? But we have to start from a catalog of galaxies. I can discuss more. This is the footprint. So we observed galaxies in this region in the sky. This is declination. This is right ascension. And we have an area for year 3 of the whole, 5,000 square degrees. There were different, the year 1 was less, and then year 3 is almost the whole area. So this gold sample catalog, this gold catalog was used to produce what we call science-ready catalogs, which are catalogs of the shapes of galaxies, catalogs of the positions of the galaxies, and a third catalog which is optimized to look for baryon-acoustic oscillations. And this is the problem, the redshift, this is uncertainties. So this is the redshift distribution, and there are uncertainties in here. And here you can see that we have 6 redshift beams. So this is the number density of galaxies as a function of redshift, and this is the redshift beams that we are using in order to do our analysis. So this is, we have one for 100 million, and then there's more strict requirements for the positions of the galaxies. I can explain this better. So this was the, then I tell the results of dark energy survey soon enough, I hope. Now, just a couple of slides about the next kid on the block is the legacy survey of space and time. It's a 10-year survey that will start next year. It will be conducted at the Vera Rubin Observatory. So actually the name was given a couple of years ago. It was very appropriate to pay tribute to this great astronomer, Vera Rubin, which you probably heard from Mustafa's talk. Had a very important role in finding evidence for dark matter from rotational curves. So it's called the Vera Rubin Observatory. That's also in Chile. The same Cerro Tololo International Observatory is in the next mountain from, no, there are 2 big mountains. One where is dark energy survey, the other where is the LSST. So it's a brand new telescope, and it's called the Simony Survey Telescope because this guy Simony donated money. called Simony. It's an 8.4 meter primary mirror with almost 10 degrees square degrees field of view. We have a very large digital camera of 3.2 gigapixels. It's being built at SLAC. It's a national laboratory in the US. It's ready and almost ready, but it's still there. It's going to be shipped to Chile at the end of the year. And right, so we plan to start observations next year. There are 8 science collaborations in LSST. So LSST is not only about dark energy. You know? There are many sciences, many different types of sciences that you can do. And there are self-organized science collaborations. And the dark energy one is the one that I participate. It's called the Dark Energy Science Collaboration. So this is a desk with more than 1,000 members. Okay, this is the organization desk. And what is really important that I should stress is that we have a participation of Latin America scientists in LSST. And this is really great. So Argentina has joined LSST. You're from Cordoba, you know that. So this is really great. And Brazil is part of LSST. Chile is by default part of LSST. And Mexico is also part of LSST. You know that? Now you know. Now you know. So yes. So this is incredible, and we are planning to organize an LSST in Latin America series of workshops, maybe starting next year. So the next lecture, I finished my last lecture. The next lecture, I will talk about photometric surveys in more detail. So yeah, I don't have much time, I suppose. I think it's already downloaded. So just look at here. Yeah, exactly.
Martín. Can we move on anyway? Sí, en YouTube ¿está viendo? Sí. Okay, cuando
It's the five.
the 5, sorry.
Yes. Thank you. Okay, so let's start the last lecture. And the last lecture, I will show you how do we find the best model of the universe and some of the DS results. How do we get there? So how do we find the best model of the universe? I'm going to describe very briefly, and I'm sure you're going to see much more detail next week, what we do, which is a likelihood analysis. I will describe the observables we have in photometric surveys, which are basically the angular correlation function of clustering and the angular correlation function of shapes. And then I discuss briefly the theoretical modeling of these observables and how to compare the experiments. Okay, so likelihood analysis. So again, the main goal that we have is to find out what is the best model that describes the universe. How do we do that? So easy, very easy. You pick an observable, a probe, okay? Choose an observable. I don't know, clustering of galaxies, you know, angular correlation function, let's say. Then you pick a model, choose a model, have to choose a model. Say lambda CDM. Then you compute the predictions from the model, and the model, of course, depends on a given set of parameters P. So these are the parameters that determine the model. You compute the predictions, then you get some data, compare model predictions with data, and you find the best model with the corresponding values of parameters. That's easy, right? This is physics 101. So the idea is simple. Details are complicated. So let me show the details now. So we put everything together in this so-called likelihood function. So we assume that the data is Gaussian distributed, and this is the likelihood of the parameters given data. So here we have, yes. In order to write the likelihood like that. So this is a quadratic function, as you can see. For the data, we always assume that it's Gaussian distributed. So the data, like the angular correlation function, etc., has some errors, and these are the errors are not Gaussian, but this likelihood is for a distribution that is Gaussian. No. Yes, central limit theory plays a role here, of course. So you have lots of data, and then the central theorem limit plays a role. But it's important to mention that although the likelihood is Gaussian, the errors are not Gaussian. Okay, the covariance matrix does not need to be Gaussian. And we take that into account. So this is a likelihood. This is the observable that you're considering. It's all here. And this is the data that you have. And this is the theory prediction. And this is the estimation of the uncertainties, called the covariance matrix. So the theoretical prediction depends on the model that you pick, the parameters. It depends, the observations depend on what experiment you're talking about. The covariance matrix reflects the uncertainty in the experimental measurement. And it's very important to have a good quantification of the covariance matrix. And the best model is the model that maximizes this likelihood function. So what we actually do is that we explore the probability distribution of these parameters given data using a Bayesian technique called Markov chain Monte Carlo. So MCMC stands for Markov chain Monte Carlo. And I have seen many plots using MCMC in the posters. So I'm sure that some of you at least know what I'm talking about. So I'm very impressed that people are already using this. So we estimate the parameters using this Markov chain Monte Carlo. We need to know, what we have in the end is this thing called posterior distributions of the parameters. And I talk a little bit about this later. So it sounds pretty easy. And then we go to more details. So what are the observables that, so I'm focusing on photometric surveys like the dark energy survey and the future LSST. So what we have is basically two types of information: the positions of the galaxies that we call clustering, and the shapes of the galaxies that we call shear. And each galaxy comes with some photometric redshift information. And this is very difficult actually to find the redshift from these 5 or 6 filters, different colors. There are several different algorithms to estimate the redshift. It's a major undertaking. And some algorithms that are used in DS is something called red magic or DNF or something based on self-organizing maps. So there are different algorithms. And then, of course, you have to decide which one to use based on some spectroscopic surveys. Okay. So the redshift information is then contained in these redshift distributions that I already shown. And so we have the redshift distribution for each redshift being. This has to be measured, and there are some uncertainties that you can see in the bands here. So what are the observables that we're going to look at? Are the angular correlation functions for different redshift beings. Angular correlation functions of what? Of the positions of the galaxies and the shapes of the galaxies. So actually there are 3 types of correlation functions. A correlation function between the 2 positions of galaxies, a correlation function between the shapes of the galaxies, and then a mixed one between positions and shapes. So there are 3 angular correlation functions. And the jargon for this is 3 times 2-point correlation functions that we are using. So let me talk a little bit about the angular correlation functions. And again, I saw posters. Your poster has done exactly what I'm trying to show here, that we estimate what is the angular correlation function for galaxies, so position. These are fluctuations in the number of galaxies at separated by an angle theta. And this is the angular correlation function. I and j will denote here different redshift beams. So in the measurements that we do, we pixelize the galaxy catalog. I don't know if you know what pixelization is. There are ways of putting this information in discrete pieces. It's called pixels. And then, there's a famous code called HuPix that everybody uses for this, even for CMB. And then we can estimate these angular correlation functions with this easy formula here, just looking at number of galaxies in pixels I and in pixel alpha, in 2 pixels alpha and beta, for instance. Okay, so this is an estimator of the angular correlation function. So that's how you estimate. There are other estimators. We use the Lundy-Saleh, but this is all type of equivalent estimators. So the measurements must be corrected, and this is the details. And the details are simply essential here, because there are many systematic effects that you have to take into account when computing these correlation functions. For instance, things that you wouldn't think about, but if you look at galaxy here and a galaxy there, it could be that the atmospheric conditions in this direction is different from the atmospheric conditions in that direction. And that introduces an error that you have to take into account. And there are many different errors, different exposures, etc. So it's very tricky, and without correcting for these systematic effects, you simply get a wrong result. Yes?
Like the CMB mask to put in CMB maps to extract the residual contamination.
Yeah, so yes, so you have to extract foregrounds, etc. We have a mask also, because we have a finite survey, and the mask takes that into account as well. Sometimes you have to block a whole region in the sky because there's a bright star that you have to block that region because you cannot see the galaxies near there. But this is the type of result that you get. So this is the angle θ is plotted like theta times w, because it's an easier way to see. And what you see here is the results from the dark energy survey, actually. These are the results from the measurements. And this is, so you can see that without the corrections, it's the red points, and they're very off. But yeah, so this is the data that we have to deal with. And the black curve is the theoretical prediction for the best fiducial model. Now you would see that there is these gray regions here. And these gray regions are the regions where we don't trust our model, and we don't take those regions into consideration when doing the analysis. So in addition to the angular correlation of the positions of galaxies, we also do angular correlation of shapes of galaxies. Why is that? Because shapes of galaxies can be distorted by matter between the galaxy and us. This effect is called weak gravitational lensing. It's a small effect. You can see this. You have seen this. This is the James Webb Space Telescope Deep Field. You see this very distorted shapes of galaxies, right? Because there's a huge mass in this cluster. So you can see by eye here these distortions of galaxies, and they have they have a direction here. They are all in this circular way, right? So this is a very strong effect. So we're looking for much weaker effects in the distortion of galaxies, and that has to do with distribution of matter in the universe. So I'm not sure if next week there will be a course on weak gravitational lensing, but this is a whole area that is very important, and I cannot do justice, of course, but just to say that the weak gravitational lensing can be characterized by magnification of the image, which is called the convergence, and distortion of the image. So you can have either magnification or demagnification, and you can also have a distortion of the original shape. So in this plot here, which I took from a thesis, is the original shape is a circular shape, and you see what happens if you have either convergence, positive or negative, or what is called shear, gamma 1 and gamma 2, that takes the sphere and distorts it like this or like that, or 45 degrees. Okay. So this is the effect of weak gravitational lensing. These are very small effects, and we can measure this in ds. We measure the ellipticity of a galaxy, but then we have to know what is the original shape. We don't know what's the original shape. So there's a whole methodology here to determine what could be provoking the change in the shape of the galaxies due to the weak gravitational lensing. So yeah, I'm not going to have time to go into details, I'm sorry.